Okay, next lecture. This one is going to be kind of heavy. It's really important. And so pay attention really well. We're talking about electrons and covalent bonds. Okay? And the readings are only two, but I'd like you to put a special effort into getting this particular aspect because this is how you'll be able to explain covalent bonds to your neighbor. Okay? It's all about electrons. I say electrons are where it's at when it comes to understanding biology, and that is absolutely true. Now, in the previous lecture, we said that we called them electron clouds, right? Which kind of, to me, it's not really accurate because it kind of suggests the electrons are kind of like floaty in clouds, not really structured, kind of chaotic. And that's not true at all. In fact, one of the first things you need to get your mind around is the idea that we've got these things called electron orbitals, which kind of takes us back to the idea that the electrons are spinning around the atomic nucleus in the same way that, like, the planets spin around the sun in orbits. It's not a circular or elliptical or two-dimensional orbit. It's a three-dimensional orbit, and they're not always spherical. And so I'll leave it to your chemistry instructor in the future to explain to you what the actual shapes are of these electron orbitals. For our purposes, I just want you to kind of understand the idea that we've got different levels. There's orbital number one, it's the lowest energy level. And then once we fill up orbital number one with the electrons, with 2 electrons that we have, we'll move up into the second and third, fourth, potentially higher energy orbitals. Okay? And I'm going to shift over to my other share here, which is going to be the textbook. And just reminding you that we have a textbook that you can be reading. In fact, you should be doing the reading ahead of time. And as you scroll down, you come down to this beautiful diagram. And this is kind of like, this is a cruxy diagram for us here because it tells us, it gives us, let me identify it. It's called a Bohr, B-O-H-R diagram. And what it does, what the Bohr diagram does for us is it shows us the location of the electrons. It's not completely accurate representative, but it allows us to get a nice representative picture. It allows us to picture the location of the electrons so that we can understand the process properties of atoms when it comes to their covalent bonding. Right? And so this is actually telling us, if you scroll down, it'll tell you that we're looking at a carbon atom here. It's carbon. So being carbon, it's going to have 6 protons and 6 neutrons in its atomic nucleus. And we also know that there are 6 electrons that are going to go into the electron cloud or electron orbitals. And so this is the first orbital right here. It's the first or lowest energy orbital. And that first orbital is going to take up to 2 electrons. So orbital number 1, first, it's going to take up to 2 electrons. And so we're basically putting electrons 1 into that first orbital, which basically leaves us with 4 additional electrons. And the additional electrons, the other 4, are going to have to go into the second orbital. Okay? And second orbital can take up to 8 electrons. But the thing is, we only have 6 electrons total, and 2 of them are going into the first orbital. So what the Bohr diagram is showing us is that in a carbon atom, we've got 2 electrons in the first orbital, and we've got 4 electrons in the second orbital. All these 3, 4, 5, and 6. And that kind of accounts for all of the electrons in a carbon, right? And this is a carbon atom. And we know that atoms don't hang around as atoms. They're going to be forming covalent bonds, but we're getting to that. Okay? And so if we, let me erase this, here, drawings. And now, if we look further down, we have a nice little diagram that shows us the Bohr structures for all of the pretty much all of the elements that we care about, plus a few that we don't care about so much. I mean, at least not in the context of biology, right? And so if we're looking at hydrogen, remember hydrogen is atomic number 1. There's only 1 electron, and that 1 electron is going to go into the first orbital. Helium, He, has 2 electrons, and its electron cloud is complete. Notice that when we get to helium, we've got 2 out of 2. In other words, we've got a complete electron shell. Complete outermost shell. The outermost orbital is called the valence shell. And so if you have a complete valence shell, this gives you a particular level of stability. So helium, you would say, is a very stable compound. It's a stable element. It has no tendency to form covalent bonds because it doesn't need to. It's got a complete outermost electron orbital. Most elements do not have complete valence shells, and so they're going to be undergoing some chemical activity, right? So if we move on to element number 3, 3 protons. In lithium, 3 neutrons, the 6 total atomic mass-bearing structures in the lithium nucleus. There are 3 electrons. 2 of those are going to go into the first shell. The 3rd electron is going to go into the 2nd shell, right? And we'll skip a couple. And now we get to carbon. This is the one that we're looking at before, with 2 electrons in shell number 1, 4 electrons in shell number 2. We go to nitrogen. Remember, nitrogen is atomic number 7, and so it's got a total of 7 electrons. 2 electrons are going to go into the first shell. 5 are going to go into the 2nd shell. And oxygen, 6 electrons in its 2nd shell. Fluorine is the next one after oxygen. It's got 7 electrons that go in its outer shell. And the next one up, the atomic number 10, element number 10, is neon, that gas that are in the shell, in the signs in the Las Vegas Strip, or at least they used to be. Right? So neon is a gas. Neon is also an elemental gas. It's just neon, single atoms of neon. Remember I said that there are some exceptions to atoms not wanting to stick around by themselves, right? Well, those atoms that have complete valence shells, they're perfectly happy to stick around by themselves. They don't need anybody. They're completely independent players. They don't need to interact with anybody, right? And so if you look at neon, it's got 8 out of 8. It's got 2 out of 2, obviously, in its first electron orbital, but everybody here has that. Right? Neon's got 8 out of 8 in its valence shell, its 2nd shell, its outermost electron orbital, and therefore it is complete as well, and it has no tendency to interact. Okay? And so forth. And I'm just going to have you look at the next one up, sodium, which has got atomic number 11, right? Sodium 11. Sodium actually has 11 protons in its nucleus. Typically, we have 12 neutrons, giving us a total atomic mass of 23. But sodium is also going to have 11 electrons, and the 11 electrons can be placed pretty much the same way that we have with neon, but that 11th electron, this one here, is going to be in its outermost shell, which is going to be the next shell out, right? And it's going to be nowhere near complete. It's just going to be an electron in that high energy shell that's pretty far away from the atomic nucleus. Okay, getting that? Yeah, and so these Bohr diagrams are really kind of cool because they, we're not going to draw Bohr diagrams for most of our chemistry lessons. We're just going to move into other kinds of diagrams. We'll be using the Bohr diagrams only to understand the process of covalent bond forming, right? Now, let me erase my markings here. Okay. And I think, let's see, are there any pictures? No, we have to go on to the next chapter. And here's where we talk about covalent bonds, and it gives us some terminology. We'll be looking at that terminology. And I think we'll be coming back to this diagram. I'm going to go back to my first share so that I can draw you a picture of the process of electron forming. Okay, and so where are we in my outline? And we talked briefly about, electrons being where it's at. We talked about these structured orbitals, not really clouds. Bohr diagrams are the things that we use to help us picture the way the electrons are sitting around atoms and in molecules in which we have got electron sharing. We've got small elements like hydrogen and helium that only have 1 or 2 electrons, and they can just deal with that first electron orbital. But anything bigger than that, right? If you go past helium, you get to lithium. Not too important. We get to carbon, that same line, and then with carbon, nitrogen, oxygen, then fluorine and neon. We've got different elements, different atoms that have increasing number of electrons, and they're going to be filling that second shell as we go along. And then when we get out past neon, there's just one more that we want to look at, which is sodium, right? This is a key concept here. The idea that stability is maximized when the electron orbital is at its capacity, not when an electron orbital, when the valence shell. Okay, so I could, let me correct this. Turn this into a highlighter. And so, yeah, not when any electron orbital. What I mean is the outermost electron orbital, which is called the valence orbital or the valence shell. Okay, because if you have a complete valence shell, you are inert, you are complete and completely stable. Right? That's good. And the next step beyond that is to get at the question, why do some elements like sodium readily form an ionic state, right? And so what I want to do with you now is to take you into a picture sodium, if you will. Okay? And so a sodium is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 proton, 10, is that 10? It should be 11. 11 protons in the nucleus. I told you that we're going to have 12 neutrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 neutrons. We're talking about sodium here, and A, sodium. It's one of those elements that don't have a symbol. That's the first letter of their name. Okay, sodium is the name in English, and I think the name in Latin is natrium, which is why it has the name Na. Okay, and now we're going to be thinking about the electrons. The electrons are going to be out here, and so we'll have orbital number 1. We'll do a Bohr diagram. Orbital number 2, and orbital number 3. Okay, and if we're just talking about sodium, the the element, we know that we're going to have 11 electrons, and you'll say 2 of them are going to go into the first orbital, 8 of them are going to go into the second orbital, right? It's 8. And then 1 extra electron, the left electron, is going to go out here into that third orbital. And then that would be sodium, the element, the atomic sodium, right? Now remember that stability comes when the electron shell on the outside is complete. And we don't have that in the case of sodium. Now, visualize this. The easiest way for sodium to have that complete outermost shell, it's really easy. All we have to do is to get rid of that third orbital. Get rid of the orbital, get rid of the electron, and now we've got 8 electrons in its outermost shell, right? Okay, and so what I've drawn for you here is a different structure. This is a sodium ion, right? If we have 11 protons, 12 neutrons, that would give me a sodium nucleus. But if we only have 10 electrons, because we got rid of that outermost shell with the single electron in it, we have 11 positive charges, 10 negative charges, and so there's an imbalance of -1 net. Of -1. And so what this structure here, this is the way that I've drawn it here, we call this a sodium ion, Na+, right? And that's the way that we'll be representing an ionic structure, okay? Sodium ion, right? And so we'll use this term, and the ion, the fact that we're saying ion here allows us to distinguish between sodium ion, which is the stable structure with a positive charge. It's completely stable, even though it's got the wrong number of electrons, right? Versus sodium, sodium, elemental sodium, which is actually kind of a metal. It's a soft metal, and it's explosive. It's really, really dangerous. It'll catch fire, and it'll be practically impossible to put out, right? And so sodium, the elemental sodium, is highly unstable, and we hardly ever see that because it's so unstable. Sodium ion, on the other hand, it's there all the time. And sodium ion, it's together with chloride ion to give us sodium chloride, and that's regular table salt. We use that all the time. Right? And so, yeah, why do some structures form ions? Well, it's because of that same issue. It's having a complete outermost shell. Okay, this complete outermost shell here. We call it a valence shell. The complete valence shell is like nirvana to an atomic, to an atom, right? And so it would the sodium would much rather sit around with the wrong number of electrons because it's got a complete valence shell when it does so, as opposed to actually having the right number of electrons and having it out in this stupid extra structure, in this extra orbital, okay? It could go in the other direction. So, I mean, the other atom that we talked about, let's see if I can do this gracefully. No, I'm not going to do it gracefully. I'm just going to add another diagram here. So if we look at fluorine, okay, which is atomic number 9. Okay. So it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 protons. I think it's got, maybe it has a different number of neutrons in it, but let's say it's got 9, 3, 4, 5, 6, 7, 8, 9. And so it's got its nucleus. And we also note that in its electrons, it's going to have electrons green this time. It's going to have electrons to put in its first orbital, electrons put in second orbital. We don't need to worry about a third orbital because we can account for all the electrons with just 2 orbitals, right? And so with 9 electrons, we can put 2 in the first orbital, and the other 7 are going to have to go into the second orbital, right? And so at this point, you could say, well, this fluorine has 7 out of 8 electrons in its outermost shell. It's got 7 electrons. The capacity is 8, right? And one way that fluorine can become stable, can reach that nirvana state of having a complete outermost shell, one way that could happen would be for it to pull an electron from somebody else, right? So I'm going to do this in different colors. So let's say there's somebody over here that's got an electron that could be taken up. And if we were to take that electron away from this original owner, okay, so let's say this is an original owner. Of the electron, right? This electron that we're looking at here, if that electron gets pulled off of the original owner and now becomes structured, becomes a part of the electron cloud surrounding the fluorine, at this point, this fluorine has 9 protons, but now it's got 10 electrons, and therefore it's going to have a net charge of -1, right? So now what we're looking at with the extra electron, we call this F minus, right? Fluoride ion. It's got a negative charge, right? And so yeah, this fluoride ion is far more stable than fluorine, the atom, because fluorine, the atom, doesn't have a complete outermost shell. Okay? With that. Okay, now I want to introduce one more bit of lingo for you because this is something that you gotta know. Sooner or later, you're gonna have to talk about oxidation and reduction. And they have to do with the movement of electrons. Okay? So in this case, an electron is moving from the original owner over onto fluorine. When the fluorine takes on the extra electron, it becomes a fluoride ion. And so in this case, you would say the original owner is oxidized. By the fluorine, and you would say fluorine is an oxidizing agent. Okay. So oxidation is a loss of electrons to something that is a different structure. The oxidizing agent is pulling the electrons away from an original owner. That original owner has become oxidized, which is serious stuff. I mean, oxidizing agents cause bad things to happen. I mean, a lot of anti-biological agents like bleach have their work by oxidizing the structures that they come into contact with. Hydrogen peroxide kills bacteria by causing massive oxidation, right? And so these are real things that occur, right? Reduction is the polar opposite. It's the inverse. So reduction is the gain of electrons, right? It's a little ironic that reduction, which we normally think of as getting smaller, in the case of reduction, we're actually picking up additional electrons. Right? And you could actually say that the original owner, the electrons that are going off of the original owner and onto fluorine are causing the reduction of fluorine into fluoride, right? And we're picking up an electron here. You could say the oxidizing agent is reduced by the process of electron moving. Okay. So that's, I know, a little bit of terminology for you, but notice that we'll be using these terms again, right? Oxidation, reduction, real standard terms in science classes. Okay. So you've got some elements like fluorine that have a tendency to form negatively charged ions. If you're negatively charged, we call that an anion, negative charged. Whereas if we have a positive charge, we call that a cation, right? It's like cat ion. Don't say cation or cation, right? It's cat ion, right? Like the ion of a cat. And so things like sodium are going to be tending to lose that extra electron to form cations. That's why sodium forms sodium ion, potassium forms potassium ion, K is potassium. While fluorine is a tendency to form anions like fluoride ion. Chlorine, Cl, tends to oxidize other things. It becomes reduced, picking up an electron to form chloride ion, Cl minus. Okay. And if you look in the human body, you'll find chloride ion and potassium ion and sodium ion in their ionic states, not in their elemental states. Right? Got that? Okay. Let's see where we were. Back to my original share. Oh, not the original share, the other share. Okay. And we're looking at, we're still talking about atoms there. But the other thing that we're looking at here is the formation of covalent bonds. So let me go back to that first share again, sorry. I forgot that we never actually got a chance to talk about covalent bonding, right? So yeah, we can check off this. What is some elements form ions? We can talk about oxidation and reduction. We've done that, right? And now we're ready to start thinking about these big questions like covalent bonds. Why do covalent bonds form? Why do the atomic nuclei stay close together when they're bonded? And it all has to deal with sharing electrons, right? So, put that little algorithm in your brain. When you hear covalent bond, you think electron sharing as the mechanism. If you hear electron sharing, you're immediately thinking covalent bond as the thing that we're talking about, right? And it is, in fact, the basic thing that holds together most all molecules in the structure of biology. Yeah, there's some ionic things and some other kinds of weak interactions. But if you look at the molecule of H2O or CH, CH4, methane gas, it's a real easy one, we'll be talking about it. The thing that holds C and the carbons and the hydrogens together in CH4 is exactly the same kind of covalent bond we'll be talking about now. Okay, how do covalent bonds form? Glad you asked. Okay, so let's go over to one more and we'll look at something familiar to you, water. We know that's two hydrogens and one oxygen. So if we draw the Bohr structure of the oxygen, oxygen is going to have 8 protons, 8 neutrons in its nucleus, and then we'll have a shell, first shell surrounding the oxygen with 2 electrons, and the second shell is going to be forming around that higher energy shell, and it's going to carry 6 electrons. Go ahead and put those electrons in. 1, 2, 1, 2, 3, 4, 5, 6, right? Got that? So, did I count that right? 6 electrons, 6 protons, 6 neutrons. Now, we talked about ionic formation before. Oxygen's not going to be able to, I mean, theoretically, yeah, you could take oxygen and have oxygen oxidize something to become O2 minus. We might call, if that happens, it's got a name, it's called superoxide. Right? But that's a little bit more complicated for us. Right now, we're thinking about, well, why do these oxygens form covalent bonds? And let's go ahead and make another atom on the board. This is going to be hydrogen. Okay. And hydrogen, as you know, we talked about this in the previous lecture, has only one proton in its atomic nucleus, and then outside of the atomic nucleus, there's an orbital, and it's going to have exactly one electron in its outer orbital, right? And now, here's the thing, right? You could sort of see that there's a little vacancy, right? There's a little vacancy right here where we could fit one more proton into the hydrogen's outermost shell. There's another vacancy here where we could put another electron into the oxygen shell. We could actually put two there, right? But we're just thinking about that one oxygen, that one electron that could be put in that space. Now, if we were to move this hydrogen nucleus over here, let's put it around here, right? And now we're going to be having this proton, hydrogen nucleus, sitting close enough to the oxygen such that its electron is going to be overlapping with the oxygen's valence shell. And oxygen's electron, one of oxygen's electron, is going to be sitting right where it needs to be kind of fitting into the outermost shell of hydrogen. Yeah, isn't that kind of neat? I think that's awesome, right? And so that could happen over here. Could have another hydrogen forming another covalent bond over here, and that's exactly what's happening. Basically, having an overlapping of electron shells. So we've got hydrogen over on left. This is another hydrogen over here, and it is forming a covalent bond. This pair of shared electrons. This pair of shared electrons right here is a covalent bond between oxygen and hydrogen. This covalent bond here is a pair of electrons shared between oxygen and hydrogen. And then we would be able to draw this same molecule as an oxygen, just the symbol. Little line corresponds to the covalent bond shared with the hydrogen. And the line over here represents the covalent bond shared with another hydrogen over here, which is going to be the same as H2O when you just write out the chemical formula. Okay. So again, think about the questions. Why do covalent bonds form? Well, it's because covalent bonds allow atomic nuclei to think that they actually have a complete outermost shell. They actually do have a complete outermost shell, but not with only their own electrons. They're actually using some of their own electrons, some of another atomic nucleus's electrons, but because we're staying just close enough in the right position, we're going to end up being able to claim electrons in the valence shell for both atoms. Okay. So that's one type of covalent bonding. You can look at other kinds of covalent bonds. In fact, we're going to be looking in the textbook next. And so you could have a hydrogen bonding with a hydrogen, right? H2. In fact, when you hear hydrogen, hydrogen gas, right? It's not hydrogen H, it's actually hydrogen H2, right? And so what we're thinking about there is you've got that same proton, and the proton has an electron shell. The electron shell is overlapping with another hydrogen. And so here are the electrons that are shared between the two hydrogens. And that would be the same, that would be the basic structure of an H2, right? If you have oxygen, O2, and you hear oxygen is what you breathe. You need oxygen in order to drive your metabolism. If you don't have oxygen, you die. We can say, well, I never run out of oxygen because I've got water, and water's got a lot of oxygen in it, right? No, when you hear oxygen, what we really mean is O2. O2. That's the substance that we need to breathe in, and it's going to have a molecular structure. If we draw the picture, we actually put two lines in between the two oxygens like that. It's not an equal sign. This is a double covalent bond. Double bond. Okay. Which is just another significant structure, but it's not that difficult to envision, right? If you say, well, here's my oxygen nucleus for here with 8 protons and 8 neutrons, and we've got that first shell and a second shell. Okay. We've got another shell over here that's overlapping. There's another oxygen nucleus with 8 protons and 8 neutrons, and it's got an electron orbital on the inside. And we now can draw the electrons in. 1, 2, 1, 2. Those are the ones that are on the inside. And then oxygen is going to have 1, 2, 3, 4, 5. Oops. Let me undo that. Those electrons in the way that I'm supposed to, right? So 1, 2, 3, 4, those are electrons that are on the oxygen's own. And then we got 5 and 6, right? This one's got 1, 2, 3, 4, and it's got 5 and 6, right? So you see what's happening? We actually have 2 pairs of electrons being shared. This pair over here is being shared. This pair over here is being shared. And we end up with a double covalent bond that keeps these 2 oxygen nuclei close together. Right. Another kind of bond that we'll be talking about is the kind of bond that occurs between carbon and hydrogen, carbon-hydrogen bonds. And so we'll be looking at methane gas. Methane is the chemical name. It's a gas. It's got the chemical formula CH4. And if you think about it, yeah, that makes total sense, right? Carbon nucleus in the middle is going to have 6 protons, 6 neutrons. It's going to have an inner shell. It's going to have 2 electrons. An outer shell. It's going to have 4 electrons. I'll go ahead and draw those in. 1, 2, 1, 2, 3, 4. Okay. Nothing new there. Okay. Now, in order to complete its outermost shell, carbon has to form a total of 4 covalent bonds. Okay? They could be double bonds, it could be, but we've got positions for vacancies for electrons and 4 of them in that spot. And so we can fill those vacancies by having the interactions with hydrogens. Remember, these protons, these single protons are actually hydrogen nuclei, and the hydrogen electron orbitals could be surrounding them. And so here's the hydrogen nucleus, hydrogen electron. Here's hydrogen electrons, hydrogens electrons, and hydrogens electrons. And so basically, a molecule like methane is another covalently bonded molecule. This process of electron sharing is exactly what keeps covalently bonded molecules together. Okay? And another thing to keep in mind is that, yeah, it's not only keeping them together, these are making the atoms happier. They're more stable, right? Why are they more stable after the formation of a covalent bond? Yeah, it's because without the covalent bond, the hydrogen does not have a complete valence shell. The oxygen does not have a complete valence shell. After the covalent bond forms, both of them are moving closer to having a complete valence shell. Hydrogen gets there, right? Oxygen is taking one step towards having a complete valence shell for each hydrogen that it forms a bond with. And as a result, it ends up being a stable molecule. Now what you can think of here is, well, what I'm seeing is a good rationale for understanding why carbon always forms 4 bonds, right? Well, it's because carbon has 4 electrons in its valence shell to begin with, and it needs 4 more electrons in order to make that complete valence shell. Okay, so the fact that carbon needs 4 more electrons is going to lead us to having the capability of carbon to form 4 bonds with other things. And generally, in structures, in biological structures, carbon will always have 4 bonds. You'll notice that nitrogen is always going to have 3 bonds. Oxygen is always going to have 2 bonds. And hydrogen is always going to have just 1 bond. You can see that here, right? Carbon bonded to 4 things. Each hydrogen is bonded to 1 thing. If you look at this oxygen has 2 covalent bonds. It's getting a bond there and a bond there, whereas the hydrogen has a bond there, only a single covalent bond, 1 pair of electrons being shared. And if you work through this on your own with nitrogen, you'll understand perfectly why nitrogen always forms 3. Okay. Now there's one more thing before we end this little lecture. And that is that if you think about these electrons being shared between hydrogen 1 and hydrogen 2, these 2 electrons here, the pull, remember the electrons are negative, the protons are positive. There's going to be a tendency for the protons to pull on the electrons. And I guess the issue is, which of these 2 sides is going to pull more strongly on the electrons? Well, if you got a hydrogen nucleus on the left and a hydrogen nucleus on the right, the pull is going to be equal. Pull on electrons equal, right? If you look over here between 2 oxygen nuclei, the pull on each of these electrons is going to be equal. And because the pull is equal, the electrons are going to be evenly split. It's not like the electron is going to spend more time over on the right or more time over on the left. There's going to be an equal distribution of electrons on both sides of the covalent bond. We call this non-polar. Non-polar covalent bonds because, well, there's no difference from one end to the other, right? Now, if you look at the bond between an oxygen and a hydrogen, right? Between an O and an H. Think about the electrons being pulled in both directions. It's electrons in the middle. The oxygen pulls more strongly. Right? And so the electrons are going to be putting a little bit more time on the oxygen side of the covalent bond, a little bit less time on the hydrogen side. Right? And this is what we're going to be calling a polar covalent bond. Polar. And a polar covalent bond is going to be different from a non-polar covalent bond. And this difference is going to be completely crucial to our subsequent lectures in BIO110, right? But the idea here is, okay, so if we look at the two sides, these electrons are going to be spending more time over here, which means we're going to have a greater negative charge, a slight negative charge on this side. And because we have a positive proton over here and a little bit less time being spent by the electrons, we're going to have a positive charge over on this side, a very weak positive charge, right? And so, remember poles? Think of pole not in terms of like a flagpole or something like that. Think of like a North Pole and a South Pole, right? Where you've got a magnetic north that's negative and a magnetic south that's positive. That polarity is the kind of thing that we're talking about when we discuss polar covalent bonds. And so because we've got a slight negative and a slight positive charge, these molecules are going to be sticky to each other, and we'll be getting to that later on. This other bond over here is also going to be positive. We've got a positive side over on the hydrogen, a negative charge over on opposite of that on the oxygen side. And so we actually draw that in a chemical formula with the Greek letter delta. Okay. Delta in this case can be a very weak positive charge, delta plus, or a very weak negative charge, delta minus. And so we could draw that over here by saying, yeah, there's going to be a delta plus on the hydrogens and a couple of delta minuses on the oxygens, which means that each water molecule is going to be like a little sticky magnet. There's going to be things with positive charges that will attract negative charges, and parts of the oxygen, parts of the water where the oxygen is, where there's going to be slight negative charges, which are going to be attracted to positive charges and other things, which makes water a very special kind of substance. And that's going to be the topic of a future discussion. But here's where we're talking about covalent bonds. Might as well take this opportunity to discuss the difference between polar and non-polar covalent bonds. Okay. And so let's make sure we covered everything. Covalent bonds are atoms sticking together because they share electron pairs. Got that. It is the basis of all molecular structure in biology. Maybe not all, but the vast, the lion's share of molecular structure in biology is occurring through covalent bonds. Okay. We talked about Bohr diagrams, allowing us to picture the sharing of electrons. We also showed you some chemical drawings with lines connecting elemental symbols like C. H4 would be looking like this, where the H's represent the hydrogen, C represents the carbon, and these lines connecting them represent covalent bonds. Okay. We talked about how the number of covalent bonds that form, carbon with 4, nitrogen with 3, oxygen with 2, hydrogen with 1, is dictated by everything that we've been talking about with today's lecture. Electrons in the outermost shell, how many electrons do you need to complete that valence shell? That's the number of bonds that you form. Okay. We also talked about how The electrons that are there in a covalent bond may be pulled with equal force by both nuclei, which gives you a nonpolar covalent bond, or they could be pulled on unequally, right? And that's what gives you a polar covalent bond. And you can actually identify these pretty easily. The polar covalent bonds that we care about are between O and H, and between N and H. Because oxygen and nitrogen both pull on the electrons that they share as hydrogens more strongly than the hydrogen does, which gives rise to always a delta minus on the oxygen side or the nitrogen side and a delta plus on the hydrogen side. Okay? And the delta represented by the Greek letters, the symbols, and these are very weak spots of charge. Okay, let me just finish up by going back to the share of the book diagram. And it's showing you basically the same thing here. In other words, what I've talked about today is pretty much exactly what you've already read about in your textbook. And so hopefully my talking you through it will give you some incentive to feel better about the content and all that. Okay. I'll see you guys in lab.